All right. The main event. Somebody we know and love, Kurt Simon, is our speaker today. He has a PhD in systems engineering from UCLA. He worked for Rocketdyne on the engines that took us to the moon, then worked for TRW for 31 years, developing data systems for satellite-based image and signal collection. Is that right? Did I get that right?
Yep.
You want to add anything? You can do that when you're during your talk.
I forget anyway.
You forget. All right. Anyway, the title of his talk is Weird Science, Part 1, Cosmology. Let's welcome Kurt.
Okay, I'm going to talk about what astronomers have contributed to the understanding of the universe that we live in. I'm going to get this out of the way of my notes. I've always been fascinated by astronomy. I'm not an astronomer, but astronomy's contributions are what has made cosmology a legitimate science and has added more to our understanding of the universe in the past 100 years than the rest of history. I graduated from University of Illinois in 1962, and you may not realize this, but that was 3 years before everybody agreed that there was an origin to the cosmos, that we had a Big Bang. So the steady state theory was still quite popular at that time. Also, it was 3 years before the geologists decided that plate tectonics is why Africa seems to fit into South America and what have you. So my bachelor's education was a bit premature, I think. I concluded my career running a large organization at TRW that did ground stations for both imagery satellites and signal collection systems that I can't tell you about. That included, yeah, right. That included the Science Operations Ground Station for the Hubble. I actually did the original design for the data processing system for that. The Landsat image processing, I actually built a running Landsat image processing system that GE eventually took away from me and went and built. We did another system called GEODS, where we were looking up in the sky to see what kind of things were moving across the sky. I did the design on that thing as well. Let me explain the presentation title. Is this weird or what? I'm going to talk about some of the weird concepts that science has come up with to explain astronomers' observations of our cosmos and where the universe came from and is going. Hopefully there's time to talk about just these four. I'll conclude with an alternative concept to explain our observations that makes a lot more sense to me, and you may be surprised by. I didn't make it up. I have lots of references. There are a lot of things that science has come up with at the other end of the scale as well, down at particle physics. 53 fundamental, or what is it, 17 fundamental particles, 4 fundamental forces, the weirdness of quantum theory. I have promised to give that presentation in another couple of months. It's mostly done. And there's some real strange stuff in that, but I think there's some much better explanations than what science currently has. As I said, I'm an engineer, I'm not a scientist, so I look for things that are common sense, much like Einstein did. So we're going to talk about dark matter and other things. Dark matter. I won't say who that is, all wrapped up and having to sit there and watch. Along with antimatter and dark matter, we've recently discovered the existence of doesn't matter, which appears to have no effect on the universe whatsoever. Okay, I want to talk about the Big Bang. Almost all scientists now agree that the universe had a beginning, currently estimated at 13.72 billion years ago. Note the 4-digit precision to that. All the evidence points to a steady state universe as being extremely unlikely. This wasn't known at the time I graduated from school. They gave me a good grade anyway. I'm sure you all know that astronomer Edwin Hubble in 1923 measured the velocity of other stars and galaxies using the Doppler method and found that almost all galaxies were receding away from us. The farther away they are, the faster they're receding from us, with the proportionality being the Hubble constant, h. Actually, galaxies in our local cluster, like Andromeda, are moving towards us because it's dominated by local gravity at a rate of 170 kilometers a second. So get ready to duck. Astronomer Vesto Slipher reported the discovery 12 years earlier, but was ignored. Henrietta Swan Leavitt in 1912 discovered Cepheid variable stars that enabled Hubble to determine the expansion of the universe. George Lemaitre, who was a priest, observed in 1931 that means if you run the clock backwards, all the galaxies must have been in the same place at the same time. So that was the Big Bang. Also, observations of quasars in the early universe disproves the steady state theory. So the cosmic microwave background is a map of the intensity of the remaining radiation left over after the Big Bang, 380,000 years after the Big Bang, when the plasma soup got cool enough that protons and electrons could combine and all of a sudden light could escape. So the farthest back we can see in time is 380,000 years. There was a couple of RCA engineers who were trying to build a radio telescope, and they had noise in it, and they couldn't figure out how to get rid of the noise. They cleaned all the bat guano out of it and everything. Finally decided that it was the radiation from the Big Bang. And that's been verified by multiple systems since then, space-based, balloon-based, and what have you. And this was convincing evidence of the Big Bang in itself. The picture is of the universe at 300,000 years after the Big Bang, when temperatures were down enough for light to escape. The surprises were the nearly spatially uniform nature and minuscule variations in this picture. The difference in temperature between the orange and the black is, 0.00 something degrees. It's now microwave because of redshifting of the visible and ultraviolet light due to the expansion of the universe. The slight variations grew into the galaxies we now see, but you notice that they're in lumps. How do we explain the uniformity? Well, the lumps that are in there are farther apart than energy could move at the speed of light to equalize. So at 380,000 years after the Big Bang, places that were more than 380,000 light years apart couldn't communicate to smooth out the temperature variations. So we had to figure out, well, why is that? Well, a fellow by the name of Alan Guth came up with the idea that there was cosmic inflation. And what that means is that within the first 10 to the minus 32 seconds after the Big Bang, the universe went from the size of an atom to the size of a baseball. And it's continued ever since, but not at that rate. And it's a weird hypothesis, but it's gotten a great deal of support. And in fact, extension by others to eternal inflation, where they assume that our universe is only one bubble in that condensed out of an internally inflating bulk. That doesn't earn any points with me. That just doesn't seem logical and consistent. Inflation also explains why we have a flat universe, because it expanded so quickly. It's sort of like blowing up a balloon, and on the surface of the balloon, it looks like it's flat, even though it's round, because it's grown so quickly. Okay, what's a flat universe? Well, the universe could be open, closed, or flat. An open universe will expand indefinitely, what they call the big chill. A closed universe will go out and come back in billions of years. the big crunch. And a flat universe will go out and just stop. In a flat universe, parallel lines don't meet. In a curved universe, they do. They come back together. The sum of the angles in a triangle is 180 degrees, as we're familiar with in two-dimensional trigonometry. Normal Euclidean geometry applies. And you'll see in here in a minute that a flat universe will eventually expand to its black hole radius, and I'm going to talk about that. Okay, if we're here on the Earth looking out at the surface of last scattering, 380,000 years after, 12.72 light years, a billion light years away from us, that 300,000 light years across that surface, which is as far as energy could equalize, this stands about a 1 degree angle. If you just work out 12.72 billion light years, 300,000 light years, you get about a degree. So if you look out, if we're in a flat universe, the lines will be straight going out to that 300,000 light years, and this angle will be a degree. If we're in a closed or open universe, the lines will be curved because of the shape of the universe. Space is curved. And so that angle will be less. So what they did was they took the picture and did a two-dimensional frequency analysis on it to see how far apart the clumps were. This is a map of percentage of times when adjacent spots in the cosmic microwave background are close to each other or far apart from each other, essentially. Fourier analysis. And you can see that the peak here says that most of these clumps peak at 1 degree, pretty close to 1 degree. And that is taken as evidence that the universe is indeed flat, because as we look out that far, the lines are indeed straight. They're not being curved by a curved universe. So that gives the curvature and the mass of the universe. We throw this picture in if it comes up. This is a map in time of the universe. So the Big Bang was over at 10 to the minus 32 seconds. In the first 1 microsecond, protons formed. The next 100th of a second, nuclear fusion began and lasted for a good 3 minutes. Then 380,000 years, things cleared up. That's what was going on. If you look across the top, you had two kinds of waves coming out of the Big Bang: density waves and gravity waves. And they, of course, stretch out as they go across time. And they say that you would expect to see polarization in these waves caused by the Big Bang. And so they put satellites up, several satellites up, to measure whether or not there's polarization in the gravity waves. And I'm not quite sure what polarization in a gravity wave means, but so several ground station and space-based attempts have been made to measure the polarization. Satellites like the Planck satellite and ground station like one called Bicep 2 at the South Pole. And they were able to detect polarization, but after scientific review, they decided that could easily have been caused by galactic dust. So we have no hard evidence out of the polarization that says that the Big Bang occurred, but we have other evidence. Okay, what are the properties of a flat universe? The scientific consensus is now that the universe is flat to within a very small error. You can see what NASA said there, based largely on the analysis of the cosmic microwave background. It's also supported by cosmic inflation theory implications. Don't worry about the details of this math, but Einstein gave us an equation which is really 10 simultaneous nonlinear partial differential equations that are very difficult to solve, let alone understand, except under very simplifying assumptions. And the equation, essentially what it says is that the curvature of space, this is a tensor, which means it's got a lot of components to it, is the curvature of space is related to the mass or energy of space. And he's got another term in here that Einstein put in because he believed in the steady state theory that the universe always existed. And if he didn't have that in there, it showed that the universe was not in steady state. So he put it in there and called it the cosmological constant. When they finally discovered that the universe was expanding, he said it was the worst mistake he'd ever made, but it turned out he was premature. He just had the wrong number for it. Alexander Friedman, a Russian, solved the equation for a great deal of simplifications and figured out what the critical density, rho, was for a flat universe. This is the Hubble constant. This is the G that's in Newton's gravitational constant, and pi. So it's pretty simple arrangement. You want to remember that because I'm going to use this later. So in a flat universe, the density is equal to this. So now I'm going to talk about dark matter. Dark matter is one of these things they made up to explain our observations. And right now they measure it as 24% of the matter of the universe. And really the visible mass of the universe, both stars and gas, is only about 20% of that required for a flat universe. The way they figured it out was Vera Rubin was studying Andromeda and noticed that the stars inside and outside the center, near the center and away from the center in Andromeda were traveling at about the same speed. And if all the mass was in the center, you would expect the ones in the middle to be going faster than the ones outside, much like our solar system. And the only way to explain that was to say there was a lot of mass distributed within the galaxy that we can't see, therefore dark. We also are able to do gravitational lensing of colliding galaxies and other stars that were behind stars in the front. I'll show you what gravitational lensing here is in a minute, because that helps show that there is matter that we can't otherwise see. Did that work? That worked. Okay, gravitational lensing is, you're sitting here, there's a star over here, and there's a large mass in the middle. And relativity, or at least Einstein says the light will bend around that large mass. And so when we look at it, it looks like we're looking at something that's out here. And I'll show you some pictures of what that looks like in a minute. And they can calculate, well, in fact, if you look at some of these galaxies here that are spread out, that's because they've been warped, lensed around a large star in front of it, namely the bullet cluster. One of the things I thought of here was maybe you could make a telescope without any aberration by just using a black hole. And the details are left as an exercise.
So wouldn't that cause you to see the same galaxy in two different places?
Yes, or spread. In fact, look at this one. This happens to be a star behind, almost exactly behind another large star. And so all the light from that star got bent to the point it actually made a ring. So that's all one star, or galaxy, actually. It's not a star, it's a galaxy. It's called the Horseshoe Einstein ring. Let me show you another interesting thing that comes out of that. Okay, the bullet cluster is a couple of colliding galaxies. The gas shown in X-rays and the visible stars show the effects of the collision, while the dark matter departs. So you can see the visible stars, you can see the gas colliding, but this blue stuff is the dark matter that went through, and that was measured via gravitational lensing. So dark matter, we're pretty sure it exists. But what is it? We don't know what it is. We only know it exists because of its effect on observations. And if the universe is flat, we're missing a lot of required mass. So there are several competing theories as to what dark matter might be. It might be just modified Newtonian dynamics. Maybe our equations for gravity are wrong when you get to intergalactic distances. But every one of those they come up with violates the law of conservation of momentum. There are other things called machos, massive astronomical cosmological halo objects. Those are things like black holes and other very large objects, but there aren't enough of those to account for the mass. And the other things, WIMPs, as opposed to machos, weakly interacting massive particles that pop into existence and disappear and what have you. Tune in for my next presentation, because that gets into particle physics. And I got some ideas on that. So if I can get it to do it, we're going to talk about dark energy. This picture, I think, is out of the movie. What's the name of the movie? Bride. Princess Bride. One does not simply believe in dark energy. Well, it's all theory. Okay, evidence for dark energy. Normal and dark matter only account for about 30% of the matter energy required for a flat universe. The remainder has been named dark energy. It looks like a uniform field countering the gravitational attraction of normal and dark matter. In fact, it looks like a non-zero cosmological constant in Einstein's equation, but moved to the other side of the equation. It's currently unknown what the dark energy is, but there are a few theories. Quantum theory and particle physics predict particles and antiparticles that briefly pop into and out of existence. This has been measured in the details of the allowed energy levels of electrons in hydrogens, so they do exist, but their effect on expansion is not known. The second Friedmann solution to Einstein's equation shows that the repulsive component of the vacuum energy is 3 times stronger than the gravitational attraction of the mass density rho. Thus, it predicts an accelerating expansion. Determining the vacuum energy is the problem. Okay, how do we measure the expansion of the universe? Well, we use supernovas. There are multiple types of supernovas. Type 1a is a binary system where one of the stars is a white dwarf. In other words, it's ceased nuclear fusion. The white dwarf accretes mass from the companion until it reignites and triggers a supernova explosion at a predetermined amount of mass. So astronomers figured out in the early 90s how to use type 1As as standard candles. In other words, stars whose brightness indicates their distance. There were 2 teams that competed with each other to measure this expansion. Supernovas only occur every 400 years per galaxy. But on the other hand, there's so many galaxies out there, they were getting 1,000 supernovas a night at one point. The Hubble Deep Field actually was pretty useful. I'll talk about that for just a second. They stared at one small area of the sky for 10 days and showed that the expansion was decelerating in the early universe and is now accelerating. Let me show you Hubble deep field here. I know you've seen this.
So there's a standard explosion for when the dwarf accretes matter from, they're assuming it's all the same
Yes.
energy of explosion or brightness of the explosion.
And it holds true most of the time, but there are exceptions. But they figured out how to measure the rate at which the universe was expanding at different times, looking back in history. So let's see, this is the Hubble deep field. Up on top, you see a small portion of the Hubble deep field. They took, was it 2.5 arc minute spot in the sky where it was one of the most empty places they could see. And they stared at it for 10 days. And this is 1/24 millionth of the total sky. They found over 3,000 galaxies in the field of view. And the James Webb has found a whole bunch more. So here's one of the supernovae. And they could, over the 10 days, they could subtract one time versus another time and come up and actually find a supernova. So they were doing this to figure out how fast the universe was expanding at different times. And they're different times because they're going back so many light years. So that distance in that case is time. So our in-depth knowledge of the universe amounts to only 4% of the universe. 96% is unknown. Okay, one of the explanations for dark energy is vacuum energy. And it's been called the biggest error in science. Quantum mechanics predicts a value for vacuum energy that's 120 orders of magnitude higher than that required for a flat universe. And to show you how big a number that is, the number of elementary particles in the universe is only 10 to the 80. And this is 10 to the 120 times too big. It's been called the biggest error in science, at least in magnitude. The problem with the necessary value of the vacuum energy is not that it's so much smaller than the predicted value. The problem is that it's set to a particular tiny value, which results in an interesting universe where we exist. The predicted density of dark energy in the universe is remarkably close to the density of matter in the universe right at this time. This is surprising, as the density of matter reduces sharply as the size of the universe increases. The matter becomes more diffuse, whereas the dark energy density remains constant. So why is that come out to be just about the right size when we happen to be here?
Aren't they different units, energy and matter? So how can you equate them? Is it just through E equals MC squared?
E equals MC squared. Yeah. And that's a pretty good approximation. Okay, let's go back to what I said I was going to talk about at the beginning. Inflation, dark matter, dark energy, and black holes. And let me offer a simpler explanation to what cosmology right now is offering. Okay, let's look at an alternative explanation of the universe expansion. Much simpler concept. We start from two principles. The universe has zero total energy. The mass energy and balances the gravitational energy, which is negative. And the universe contains all that there is. Plus, we have strong evidence that the universe is flat. So from those points, Feynman pointed out that if we equate the total mass energy of the universe to the total gravitational energy, then rearrange terms, you get the eventual radius of the universe after kinetic energy dies out. Surprisingly, this radius is similar to the radius of a black hole. And so if the mass energy balances the total gravitational energy and you combine equations, you come out with the universe has got to expand to this radius, which looks like a black hole. If you're using vacuum energy instead, it would continue the expanse beyond zero total energy, and so that doesn't work. We know that black holes exist because there's lots of them out there. Sufficient mass within a given radius has an escape velocity greater than the speed of light. So anytime there's sufficient mass within a given radius, gravity will prevent light from escaping. Schwarzschild calculated the radius of a black hole as a function of its mass to be as shown here. R equals 2 gm over c squared. G is the gravitational constant, m is the mass of the universe. General relativity says that density increases to infinity as you go towards the center of a black hole, resulting in a space-time singularity, and physics doesn't like singularities because the laws of physics break down. What happens in a black hole stays in a black hole. Exactly. Black hole Sagittarius A star is at the center of our Milky Way. It's about 3 million times the size of our sun. If you look at it with X-rays, you can see a spot in the middle there. The X-ray satellite, by the way, was built by TRW. It's called Chandra. And instead of lenses, it's got metals, things to bend the rays in the X-rays. There's a recent discovery of the most massive black hole at 12 billion times the mass of the sun, and it's only 900 million years after the Big Bang. The Chinese found it with a 2.4 meter telescope, and it's been verified by others. Here's a new slide. This is Sagittarius A star as seen by an array of 8 telescopes across the world. And what it's looking at in that orange donut is the debris that's swirling around the black hole, generating all kinds of radiation. And that picture was an elaborate reconstruction of those radio waves captured by those 8 telescopes, collectively known as the Event Horizon Telescope. Well, now I'm going to tell you that the universe satisfies the criteria for a black hole. From the previous slides, we had the radius of a black hole and the density of a flat universe. Calculating the Hubble observable radius of a flat universe yields the Schwarzschild radius for the same mass, indicating the universe must naturally expand to its Schwarzschild radius. Actual estimates of mass and radius for the universe are not too far off. This says that a flat universe with zero total energy must expand to its black hole radius, and this doesn't require dark energy. Within black holes, you can show that gravity is repulsive. This implies that mass inside of a black hole will move to the Schwarzschild radius, and you end up with a soap bubble black hole, or in our case, universe. This is a different type of modified Newtonian gravity. It applies only in very small cases within black holes. And black holes are pretty small. The Schwarzschild radius of a person is less than the atomic radius. The black hole radius of the Earth is only 9 millimeters. Galaxy clusters are bigger than black holes, but the universe is not. Consequently, the mass inside of a black hole will be concentrated at the event horizon or black hole radius. This eliminates the singularity at the center and provides a firewall to resolve information loss paradox. Any information falling into the black hole gets destroyed at the radius. So what's the advantages of this alternative expansion concept? No fine-tuning problem. based on fundamental principles rather than unknown dark energy and strange inflation concepts. Quantum mechanics says that information must be conserved, but relativity says nothing can come out of a black hole. Hawking radiation is thermal and thus carries no information with it. Hawking and Susskind got in a public debate over whether information is preserved or lost at a black hole. Hawking conceded the best theory for resolving the paradox is the firewalls theory, where the information is destroyed at the event horizon because that's where all the mass is. So that gets rid of the singularity and solves the information loss paradox. You'll be glad to see this slide. The conclusions are dark matter exists and is probably the subject of particle physics. We don't need dark energy to explain the expansion of the universe. There's no need for inflation or parallel universes to explain the uniformity of the cosmic background. And black holes don't have singularities or information loss. So we live in a black hole, and all the information in the universe is proportional to the surface area of our black hole. Or maybe we're just a three-dimensional hologram of the two-dimensional surface of the black hole. I said I had a lot of references for this. Larry Krauss is an excellent writer, Universe from Nothing. Andrew Thomas has written 10 books, which are available on Kindle, which take a very pragmatic look at all kinds of things to do with physics. His second book, Hidden in Plain Sight 2, has a lot of the mathematics for showing that the universe is a black hole and the universe is flat. All of that mathematics is in there. The particles of the universe I'm going to use in the next presentation because he shows how the standard model has a much simpler explanation than wave theory of matter. Brian Greene's an excellent writer. The Weird Universe came out after I did this briefing and covers most of what I put in here. It's a good book. Got the grand design by Hawking and Wadnoff. And then there's a whole bunch of links, which I've got in here. You. And if you like, give me your email and I will send you a copy of the briefing charts with the links and the references.
I can't imagine the content of the last book before the Big Bang.
Say that again.
I can't imagine the content of the book before the Big Bang.
Well, Gribbin is a good writer also. Well, if the Big Bang took 10 to the minus 35 seconds, you know, whatever happened before the Big Bang must be shorter than that, I guess. And if you can't ever measure it or observe it or see it, what good is the theory if it has no impact on your knowledge of the universe? But the way science works is we make measurements, we come up with a theory, we beat the measurements against the theory, and if it works, then we continue to use the theory until it doesn't work anymore. Like Einstein's theory didn't work when we were trying to figure out why Mercury orbit was rotating. And so that led to the theory of relativity, general theory of relativity. So the net change to my understanding of the way all this works is that I think dark energy doesn't have to exist, that just the nature of the universe being flat and zero energy, zero total energy, you can work it out in simple equations. It should be expanding. So what's probably happening is, oh, you don't need inflation at the beginning of the universe. You've just got repulsive gravity that's pushing everything out. And it's much smoother, and so you can get the uniformity in the cosmic microwave background because things are moving out not quite so quickly. So you can get away from, nobody knows what inflation is or if it's real. They don't know what dark energy is or if it's real. I think this is a much more practical perspective on it. I strongly recommend the book by Andrews. Let me go back to that. I can get back to that. I think I just blew it. Good place to stop. The book by Andrew Thomas, Hidden in Plain Sight 2, does a much better job of explaining all this in about 10 more chapters than I did. But he's got the math and the logic and the principles to support it all. So that pretty much is.
Answers some questions? Can you go back to that, the horseshoe thing? I'm wondering if they can unbend the, unwork the, yeah, go to that thing.
Yeah, they have the mathematics to do that. Oops. They have the mathematics to do that. In fact, the way they were able to plot out how much dark matter there was in those colliding galaxies was using the same kind of equations where they go in and figure out if that light came from here and it was bent here. You know, it's very complicated mathematics, but they could go through and put that back together.
So they come up with the picture what the galaxy looks like.
Yeah, mostly.
And it'd be much brighter than without that intervening
Yes,
galaxy.
yes.
So they
There's a
can
lot of
see
stuff out
things
there.
far, far away.
I was looking for things that I might add to this since Webb launched. There wasn't much. There were they found a lot more galaxies in the Hubble Deep Field using Webb. And they got, well, the picture of Sagittarius A star, the black hole, that didn't come from Webb. That came from the Event Horizon Telescope.
So if I understand this right, you're saying gravity is negative energy,
Yes,
right? That's
because to move things that are being
right. That makes
attracted
sense.
together apart requires energy. So that's the negative.
And this is a negative force putting it together, and that all the
You add that to
energy
the mass
adds to the-
energy. The mass energy equals mc squared,
right.
and those energies have to balance. One of the arguments is, well,
In order for everything, the total energy to be zero.
yes.
Right.
So in a zero total energy flat universe, it's going to expand to the black hole radius. And it turns out that there's a factor of 2 difference between the black hole radius and the eventual radius of the universe, which says that the eventual radius of the universe is less than the black hole radius, which means it really is a black hole. So what will happen is all the galaxies will move out past the black hole radius, they'll come back in and wait
We can watch it.
for it.
Wait for it, yeah.